In the past, you've probably learned about various types of concentrations. Molarity is a common one, and so is mass percent. However, different situations demand different types of concentration units. And here today, we're going to look at the various ways in which the chemist calculates concentration. And a little later on, we'll learn about the various situations that require these different types of concentration units. We're going to begin with something that is hopefully familiar to all of you, and that is the molarity unit. Molarity is abbreviated with a capital M and is defined to be molarity is equal to moles of solute divided by liters of solution. Now, with such a definition, it's very clear that the units of molarity will simply be that of moles per liter, and we let the capital M stand for this, be an abbreviation for moles per liter. But an important thing to recognize about molarity is that volume actually depends on temperature. Most things expand when they get warmer, and the volumes of solutions do indeed increase when temperature increases. And because the volume of the solution in liters is part of the definition of molarity, the fact that the volume depends upon the temperature also means that molarity depends upon temperature. At higher temperatures, the volume increases, and with a larger volume, the actual value of the molarity goes down because the volume of the solution is in the denominator of that fraction. A good thing to keep in mind. Now, to avoid these sorts of temperature-dependent behaviors, the chemist has also invented a different type of unit known as molality, and it's abbreviated with a lowercase m. Now, molality shares some of the molarity definition, namely that the moles of solute still appear in the numerator of this fraction. However, in the denominator of the fraction, we instead have kilograms, a mass unit, not a volume unit, but kilograms of the solvent. An important distinction here is that not only are we in kilograms, but we are also referring to the solvent. And the solvent is only that part of the solution there in an excess amount, oftentimes the water, not the solute. So two very important differences. The units of molality are going to be units of moles per kilogram. And in fact, moles and kilograms are not dependent upon temperature in any way, and so molality doesn't depend upon temperature, unlike molarity, which does. All right. Now, another way the chemist expresses concentration, we often find this in the allied health field, is in terms of the mass percent. And the mass percent is given by the following little recipe. It's the mass of the solute, not the moles, but the mass of the solute divided by the mass of the solution, that is, the combined masses of the solute and the solvent. And then, to make it a percent, we multiply by 100. And although we often follow this up with the percent symbol, this is technically a unitless value. The mass, grams perhaps on the top of the fraction, cancels grams on the bottom of the fraction, and we don't have any units in the final answer. Now, we have several different situations that can develop. When concentrations are quite low, it's sometimes better to report them not in mass percent, but in parts per million. And you'll recognize that the parts per million recipe looks a lot like the mass percent, namely that we have the mass of the solute divided by the mass of the solution. That part of the recipe is exactly the same as that recipe we used for mass percent, but here's the difference. Instead of multiplying by 100, we multiply by 1 million, which is the same as 10 to the 6th. 10 to the 6th, 1 million, is what we use instead of the multiplier of 100, that which we used for mass percent. We call this parts per million, and it's used when concentrations are low. when the solute is present in very small amounts, why we'll often use the parts per million concentration unit. However, there are situations where the concentrations are even lower, very, very small amounts, and in those cases we use parts per billion. The recipe is exactly the same, except for the multipliers. You'll see we take mass of solute, divide by mass of solution, and this time we multiply by a billion, 10 to the 9th. All right, this is used when concentrations are very low. Often you'll see part per million and part per billion concentration units used in reference to drinking water, where the levels of calcium, magnesium, lead, and other trace elements has to be monitored very carefully, and where very small amounts of these dissolved solutes can make a significant difference, especially in terms of health risk. Parts per million, parts per billion, and mass percent, all basically the same recipe with different multipliers. The last type of concentration that we'll refer to is the mole fraction, often abbreviated with a capital X. And X, or the mole fraction, always refers to the ratio of the moles of solute divided by the moles of solute plus the moles of solvent. That is the total number of moles that we've got to work with. No multiplier involved. This will always be a number that is less than or equal to 1 and refers to that fraction, from a mole standpoint, that fraction of the material that's actually present of the solute. Now, it'll help to demonstrate these recipes and how they can be used if we actually tackle a problem. And that's what we're going to do next. The problem is actually pretty straightforward. It says that we are given a 3.75 molar sulfuric acid solution. Now, a little bit later on, we'll recognize that this is a number with 3 significant figures, and that'll be important as we round accordingly. This 3.75 molar sulfuric acid solution has a density, this is the density value here, of 1.225 grams per milliliter. The question is that we should calculate the solution's molality, mass percent, and mole fraction from the point of view of sulfuric acid. We're asked to convert the molarity that we've been given, 3.75 molar, into molality, mass percent, and mole fraction. Now, there is an important assumption that we have to make. The assumption that we make is that the volume of the solution is exactly equal to 1.000 and so on liters. Now, the reason we can make this assumption is that the concentration is independent of the volume that we are considering. Just take this as an example. Let's say that you bring out of your refrigerator a carton of orange juice, and then you pour some of that orange juice into a small juice glass. What you have before you is a large carton, mostly filled with orange juice, and a juice glass that has a small amount of that juice in it. Which of them has a different concentration? Which one has the higher concentration? Which one has the lower concentration? The fact is, it doesn't matter whether we're talking about a large carton of orange juice or a small glass of the same orange juice, the concentration is exactly the same. And therefore, in problems like this, it's perfectly fine to make an assumption about the volume of the solution that you're dealing with. Now, what we're going to do is we're going to determine 5 fundamental quantities that we'll use to actually answer the question. These calculations will serve as good review for you in terms of how we manipulate molarities and molar masses and so forth. Let's begin with the first conversion. The first conversion has us calculate the mass of the solution. And the mass of the solution is going to be equal to the density of the solution times the volume of the solution. And we have values for both of these. The density was 1.225 grams per milliliter. The volume Well, we assumed it was 1 liter, which is perfectly fine, but note that we have to have the volume now in milliliters units, not in liters units, and so I'll multiply this by 1,000 milliliters, which is the same thing as a liter. Doing so gives me a mass of solution equal to 1,225 grams. This is the mass of the solution, and it's a number that we'll use a little later on. But there are 4 more steps to go. Step number 2, calculate the moles of sulfuric acid. This is another value that we can determine having made the assumption that the volume is 1 liter. In order to calculate moles, we take molarity, which we know, times the volume in liters. The molarity was 3.75, and let me break that down for you. Molarity means moles per liter, and we multiply now by 1.000 and so forth liters. The arithmetic is very simple. It's simple because we chose the right volume to use for this problem, 1 liter. The number of moles that we calculate for sulfuric acid is therefore 3.75 moles of H2SO4. All right, so far, so good. Step number 3. We're going to calculate the mass of the sulfuric acid. This is going to require that we know something in advance. To calculate the mass of the sulfuric acid, why, we need to take the moles of the sulfuric acid and multiply by the molar mass of sulfuric acid. And so we'll have to use the moles of sulfuric acid from the previous step. That's 3.75 moles of sulfuric acid, and we'll also have to multiply by the molar mass of sulfuric acid. You go to the periodic table for this and add up a couple of hydrogens, sulfur, and 4 oxygens, and what do you get? 98.07 grams per mole. And doing the arithmetic, it gives us that we have 367.79, and I'm being deliberate about holding on to a few more significant figures than I actually need here because I'll be using these numbers in a calculation to come. 367.79 grams of sulfuric acid are actually present in this 1 liter of solution that we've imagined. Now, steps 2 and 3 obviously refer to the solute. Step 1 refers to the solution. We need some more information about the solvent, and that is what we get at as we look at step 4. We need to know what is the mass of the solvent. Now, recall that we actually have the solution mass. This is something that we calculated from step number 1. So I'll put a 1 right there. And recall also that we know the mass of the sulfuric acid. And so if we subtract the solution mass and the mass of the sulfuric acid present in the solution, that was from step 3, why, we'll get the difference. And the difference will be whatever water is left over. So we've got 1,225 grams of solution, and we subtract from that that part of it that is only sulfuric acid, which we calculated right here, 367.79 grams, and we get the mass of just the water, which comes out to be 857.2 grams of water. What we have here is a little bit of information about the solvent, and we're going to continue with the solvent in step number 5. All right, step number 5, we would like to know what are the solvent moles. And the solvent moles, that's just a matter of using the molar mass again. In this case, the solvent is water, and so we'll want to know the mass of the water, which we have from step 4, and we'll divide by the molar mass of water, which we can get from the periodic table. And doing so, we use the 857 grams that we had calculated in step 4, 857.2 grams of water divided by its molar mass, which is 18.01 grams per mole. And we get, in this case, with a few extra significant figures just to help us along, 47.5957, and this will be moles of water. Now, we haven't actually answered the question. Recall the question was to calculate the solution's molarity, or molality, mass and mole fraction, and we haven't done that yet, but what we do have are all of the pieces to make this work. Let's go after the molality first. Okay, we'll keep all of that on screen, and we'll refer to just the molality. And molality, in this case, will be the moles of sulfuric acid divided by the kilograms of the solvent, in this case, which is water. Be careful with this. Molality refers to kilograms of just the solvent, unlike molarity, which has the liters of solution in the denominator. Now, the moles of sulfuric acid on the top, we've calculated from step number 2. And the kilograms of water we have from step number 4, and we can actually fill in the numbers as need be. The moles of sulfuric acid, 3.75 moles. And then, being a little careful here with the water, we actually, in step number 4, calculated the grams of water. What we really need are the kilograms of water, and so I'll take the liberty of moving the decimal place for us here. It's 0.8572 kilograms of water, moving the decimal place to the left 3 places, and what we do is divide those. We wind up with an answer, which is 4.374 molal, little m. Now, throughout the problem, there has been one limiting feature in terms of significant figures, and that was the initial concentration, which was given as 3.75 molar. And so the assumption we made regarding the volume should not in any way affect the significant figures in the problem, because we can add as many zeros as we like. So we need to have 3 significant figures in this problem, and we'll need to round this off to 4.37 molal with 3 significant figures appropriately. Okay. So, of the 3 things we were asked to calculate, molality, mass percent, and mole fraction, we've taken care of the molality. Next, let's go after the mass percent. And the mass percent, recall, in this case, is going to be the ratio of the mass of the sulfuric acid to the mass of the solution. And the mass of the solution really refers to everything all added up, the mass of the sulfuric acid plus the mass of the water. And don't forget, we'll also need to multiply that by 100 to make it a percent. Taking the numbers that we have 367.79 grams of sulfuric acid, and the total solution mass from step 1 was 1,225. Multiplying by 100 and rounding off to 3 significant figures, we find that this is a 30.0% by mass solution with 3 significant figures. In other words, by mass, 30% of this solution that we're looking at, 30% of its mass is due entirely to the sulfuric acid. The remaining 70% is the weight of the water. All right, 2 down, 1 to go. The only thing that we need to look at next is the mole fraction. And the mole fraction is calculated by taking the ratio of the moles of sulfuric acid and dividing by the moles of sulfuric acid in combination with the moles of water. All right? And so we've got numbers for all of these. We have the moles of sulfuric acid calculated from step number, what would that be? Step number 2, I guess. Okay, so we've got 3.75 moles of sulfuric acid, and then we would divide by the combination of the sulfuric acid moles, 3.75, plus the 47.5957 moles of water. No additional multiplier required for that, but I've got to quickly calculate this in my notes. I didn't quite have the right answer, so let me just punch the numbers in. Let's see. We have 3.75 divided by the total of 3.75 plus 47.5957. And the mole fraction comes out to be 0. And with three significant figures, 0.730. Only a very small percent from a mole point of view is actually equal to the mole fraction of sulfuric acid. This is the mole fraction of sulfuric acid. Now, by the way, we can also calculate the mole fraction for water. You see, these mole fractions, the mole fraction of water and the mole fraction of sulfuric acid, must add up to 1. That is, there are only two things present, and each one contributes enough that the overall total is equal to 1, much like a percent. The total is always 100%. Mole fractions always add up to 1. And so if we want the mole fraction of water, all we need to do is subtract the mole fraction of the sulfuric acid from 1 to get 0.927. 0.927 is the mole fraction for water. And combined with the mole fraction for sulfuric acid, the two add up to 1, as they are supposed to. Well, there you have it. Many different ways to calculate concentration, and they can all be converted from one form into the other by just considering some simple relationships involving density, molarity, and mass.